In this case, we've been presented with a hydrocarbon which is said to have a empirical formula of C₄H₅, and we've been asked to work out the molecular formula of this particular hydrocarbon. Now, how am I going to approach this? Well, one of the first things I'm going to do is refamiliarize myself with, well, what's the empirical formula in general? What's the molecular formula in general? So the empirical formula is, in effect, the smallest whole number ratio, or some would say the simplest whole number ratio of atoms of each element present in a given compound, right? Now, we've been presented with that, but we've been asked to find the molecular formula. Now, what's the molecular formula? Well, the molecular formula gives us representation of the actual number of each the actual number of atoms of each element present in the given molecule. Okay, so we effectively need to work our way from the empirical formula to whatever the molecular formula is. Okay, so we know it's a hydrocarbon, and what I'm really aiming at doing here is effectively comparing I want to get the molar mass of the empirical formula, and I'm going to want to compare that with the molar mass of the molecular formula, right? But I don't have the molar mass of the empirical formula at this stage. But what I do have is the formula, right? So using the periodic table, I can effectively work out, or what is the actual empirical formula. So I'm going to do that now. So we've got C₄H₅. So we've got carbon and hydrogen, right? So in effect, the relative atomic mass in each given case is the molar mass of each given element, right? So what I'm going to do is I'm simply going to take that and I'm going to say, well, therefore the molar mass, Mr, of carbon is equal to 12, right? 12.0. I'm going to say the Mr of hydrogen is equal to 1.0, right? Now, what I'm going to effectively do is I'm going to need to, well, I'm going to give the units anyway. First of all, I'm going to add the units. So that's going to be grams per mole, right? In both cases. Okay, so what I'm going to effectively do is I'm going to use these to determine the molar mass of the formula. So effectively, simply put, it's just multiplying the Mr of carbon by the number of carbon. So in this case, and then adding obviously that to the Mr of hydrogen multiplied by the number of hydrogen. So this is effectively going to be 12 times, and here we can see that the coefficient with the corresponding with the carbon is 4. So we're going to use that 4, and then we add that to for hydrogen. So that's the coefficient in the case of hydrogen is 5, right? So we're going to effectively plus 1, right, from there, 1 from the Mr times 5, right? And what's that going to give us? Well, I invite you to do this calculation and see what value you get, right? Now, if you do that, what you should find is you get 53, okay? So 53, and that is going to be in grams per mole, right? So this is effectively the Mr of, actually I'll just write it below, right? So Mr of C₄H₅ is equal to 53 grams per mole. Okay, so we've now got the Mr of our empirical formula. We also, from the question which is provided, we've got the Mr of the molecular formula, and we need to, at this stage, look at working out, well, what's the difference between the two values? How do we get from the Mr of the empirical to the Mr of the molecular formula? What's the multiplier? Now the formula I'm going to use in terms of multiply determination is that the multiplier, and this is going to be critical when we're scaling up, right? So the multiplier is equal to the MR of the, I'm going to abbreviate effectively. So this is effectively the MR of the molecular formula, right? But I would just write MR molecular divided by the MR of the empirical, right? Empirical, right? And what does that give us? Well, I mean, let's set up the calculation, right? So that is going to effectively be equal to 265 divided by 53, right? Right? And if you do work that out, which I would invite you to do, what you should find is that you're gonna get 5, okay? 5. So therefore the multiply is equal to effectively 5x, okay? And what does that mean? Well, if we go over here, effectively work with that information, what we need to do is take our empirical formula, which was C₄H₅, and use this multiplier, right? The 5x multiplier on that, okay? So effectively for the carbon, that's effectively going to be 4 times 5. So the multiply, right? 4 times the multiply 5 is going to be equal to 20. And therefore we can say in the case of the molecular formula, using this scale up factor, right? Using the 5x, the multiplier, we get that it's going to be C20, okay? Now we apply the same thing to the hydrogen. So we say in the case of the hydrogen, right? With this case we've got 5, right? So it's going to be 5 times 5, and that gives us, of course, it gives us 25, right? And in this case we're going to say, okay, well, in this case the scale up factors, I mean, in this case the coefficient corresponding with the hydrogen is going to be 25, so it's going to give us H25, right? If we now go to the stage of consolidation, if we consolidate this now, what do we get? Well, we're going to get C20 H25, okay? And this is our molecular formula, okay? C20 H25. Now, this molecular formula actually has some molecules which have quite a similar formula to it. Okay, and we're going to explore that briefly, just as a bit of an extension to this, right? So if we take a look at these two molecules here, right? What this is 1,8 diphenyl octane, right? And in effect, if you were to have a go at counting some of the hydrogens, so in this case, for example, so remember the formula we calculated was C20H25, right? So, but if we look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, right? So as you see from the count, we've got 26 hydrogens here, right? Which doesn't quite match what we calculated. However, if this engages in a radical substitution reaction, if a hydrogen gets knocked off this molecule and it ends up with an unpaired electron effectively and becomes a radical, this can become C20H5, right? So in this case, we would just call it, and this is not like the IUPAC name. This is just a general name. I'm just writing here for the purposes of this example. But this here, as you can see, we've got here a radical version of it, with a hydrogen missing effectively, right? And that would obviously mean the 26 minus 1, 25. So here you've effectively got C₄H₅, right? So yeah.